Um, as I said regarding the final exam, when you come very close to the final exam, we'll cover the final exam in details. So we'll cover the final exam in details. And don't worry, there is a curve from the ACS people, as well as I'll curve it. So I'm not letting my students failing because of final exam. That's some of the stuff we did not cover. Some stuff even not in the textbook, but they want to test your response, how you respond to that. So don't worry about the final exam. Will be curved. That's all over the campuses is curved. So don't worry about the final exam. But anyway, so at least you have to adhere to the final exam dates and time. We are not allowed to give the final exam before time, correct? You cannot come to 1 or 2 days for the exam. You want to take it because you have a trip, holidays, you want to go on your vacation. No, that will not work. We have to take it in time because of the security reason of the connected to the final exam. The final exam should be secure. So it has to be taken the same time, the same spot, and it will be secure. Now, let's look at the let's look at this one here. This here, this owl, those I'm very pleased to see that's out of 19 students. We have 14 students had really entered OWL, and this is very good. As you can divide if the class the total 19, and we have 14. 14 divided by 19 multiplied by 100, I think over 80 something, 85%, which is very good. So we have only 4 students, some of whom they are still working on the glitches. Yeah, there are some glitches going on, but I think by next week, because after 2 chapters we'll have a quiz. After 2 chapters we'll have a quiz. The last exam 4 will have 3 chapters together, correct? And I will give you a lot of ACS training and practice for the final exam. Final exam is 25%, and as I said, I'm very pleased to show you the list. Your name is there, then we are pleased. So if your name among the 4, so just let me know. I can help you. We can contact the publisher direct. So other thing is to share here is the questions themselves. What I put for you, the questions here. If you look at this, the questions is divided into all this, the difficulties and everything. So if you look at those questions, it's not really difficult question. See, the problem is with the, as I said, back to the final exam, it gives you few concept exam. Those are mostly some of them concept, but the major stuff in the final exam is calculation based. So when it comes to calculation based, it eats up the time of the final exam. That's the problem we have through all this ACS exam, which a lot of faculty, they don't believe in, but we have to satisfy the people from outside. They'll come to judge our program. They have to have some sort of statistics to compare it to the national standards. So they have to compare us to something. They have to have a database or baseline. So the baseline is the national average for general chemistry 1 or principle 1. Then whatever we are doing, they are using ACS exam. So therefore, we can show the people our average. If our average is very, very low, this accreditation, called them Southern Accreditation Association, they can shut us down with the principal. So they will not allow us to teach principal until we find the remedies for this. So that's very serious. That's the reason administration put a lot of pressure on the faculty. We have to have something in our hands, data to prove how our students are doing. So if you look at all those here, let me try to get this. If you look at those, most of those here are concept-based questions. The question, I apologize. It's not Corona though. It's not COVID. No, it's just cold. There is no heat. I measure the temperature of my body. What's the temperature of the body? You are a chemist now. How much? 98. Okay, we don't have the calculator to convert, although there is a question about conversion. There is conversion stuff there. 98, how much is centigrade Celsius? 37, about 37. Somebody will ask you in the hospital, they have some nurses, they know both, bless you, they know both systems. They know the metric and know the English. So they tell you 98 or 37 centigrade Celsius. So as I said, if you look at all those questions here, the first one, those are content-based or concept-based, not that many questions. And as I said, the final exam, which we are really targeting, this final exam will be mostly, as we go in depth, you will see a lot of calculation. I'll put a lot of calculation for you. So, but the first one is mostly is concept-based. It's not really difficult. So, yes, any question? Any questions? So this one here, and let me just get out of this one here. Sometimes you have to tell the whole thing to. So I'm sharing this one here. This is the date of the final exam, so you are aware of this, correct? So just this one here, and then we'll start chapter 2. Any question about chapter 1? Any question about chapter 1? So chapter 1, let me conclude. We had, and I think I have I showed you in the hour. We have scientific method, concept of scientific method, correct? Then we had, after the scientific method, we went further and look at the matter itself, and then we divide the matter into pure substance and elements. Then pure substance can come and combine themselves, make mixtures. Mixtures can be heterogeneous or heterogeneous. And then we went to physical methods to separate those mixtures to their original pure substances. And then we went further to look at the significant figures, all the significant figures rules and application. And then we went from there, from significant figures determination and applications. We went through the density, and then at the last were temperature. So those are the topic, the most important topic of chapter 1. Chapter 2 will look into details about the, let me open this here. Share the chapter 2 is looking in details here. It's looking into molecules and ions and the periodic table and the division of periodic table. Then we'll look how to name covalent compounds. What's the definition of covalent compounds, and what the definition of of ionic compounds, correct? Now, this is, again, there's another chapter which is really concept based. However, we have one small tiny calculations in it, which is, this calculation will cover the average atomic mass appears in the periodic table. So let's start. Any other question you have? You want to ask? Any question you have? Any question? Okay. So the quiz 1 or exam 1 will come after we finish chapter 2, and they will come from whatever you are doing inside the hour. I base most of the exams and the quizzes on the online assignment, because it has no, effect that you do the whole thing and you have no use of it. So your quizzes and exam will come from OWL. And OWL questions, some of them even used by the ACS exam, but different wording, different numbers, correct? So those online questions, OWL, CHEM 101 active, web assign, all those are using using questions with the database is really taken by ACS exam and just the numbers changing. So we'll talk about molecules and ions, but before that we have to talk about the atoms, correct? So the atoms here start with the Greek, and then I think it's transferred into the Egyptian pharaohs and the old Chinese. So those are the people who are worked on the atoms. Anything, the Greek, the idea is anything is very, very tiny and cannot be broken in small pieces, that's an atom. So the word atom came from the Greek name, right? So it came out from the Greek name. So by the way, the Chinese came first through the history, then the pharaohs, Egyptians, and then the Greek. So the Greek is correct, I mean, very close to us, to the modern time. Not modern, but the Chinese are very, very deep inside the history, and then followed by the Egyptian pharaohs, which is 5,000. The Chinese more than that, maybe 10,000 back in the history, and the Greek is about, because they looked at the whatever the pharaohs did, so it's about 6,000. It's older than they came after. I mean, 4,000, maybe 3,000. But anyway, the idea of this is the atom is a small, tiny object or particle. This cannot be divided. You cannot break it. That's the whole thing about the Greek. And then it came out, and you heard about this theory of the Greeks said about that's the matter is not what we define now. They look at matter is made of fire, correct? Fire, air, and water. So that cannot be really proven, and it's just they were more philosophy than science. But we are interested in our modern nation of chemistry, which started with Dalton's. Dalton's took all the stuff from the Greek and postulated a very nice theory about the atom. However, he did not finish his postulates because he lacked at that time. The technology was not there, and there is no experimental setup to prove his ideas. So far, he did very well when it comes then to certain amount of the definition of atoms. He really could not, because it's not his problem, because at that time the technology was not there. Now we have the technology is there, so it had helped to define the atoms in much better way. So one of the postulates, he said matter is composed of small particles called atoms. We took this one from the Greek, correct? And an element is made of one atom or two or three or more. So that's good. That's very good. So, and this is characteristic for each element is made for certain amount of atom, and the ratio between those atoms is different from one to another. So, and the third postulate that each element differ in properties from atoms of all other elements. So if I have two elements, you will see those two elements might not have the same physical properties, not even the chemical properties, right? Because you will see later on the content of their inside the nucleus, number of the protons, number of neutrons, and number of electrons outside the nucleus will give the physical and chemical properties of any atom, correct? So you will see that's the characteristic of an atom is within the atom itself, not from outside. And each element will have different number of protons, different number of electrons, different number of neutrons. So, and here is giving you an example here. Atoms are neither created or destroyed within a physical or chemical change. They are not destroyed. They are still one unit. There is no half an atom. There is no quarter an atom. There is no fractional atom. There is none. What's happened is the rearrangement of those atoms during the physical or chemical change. That leads to a new rearrangement, a new element, a new compound. Correct? That's what it means. So if you have here, give you an example. We have copper 1 oxide or copper 2 oxide. So you have a copper which is golden in looking, and you have oxygen you can't see. But if you put them together, the copper will turn first greenish and then turn black. So therefore, you see, this copper oxide is no longer one metal. It's made of two elements, not one element, two elements made of copper and oxygen together. And it is copper 2. It is black. So oxygen you cannot see. So we can't see oxygen from the air. The Joseph Proust came up with the law called law of definite proportion or constant composition, and that's what I said in a change, a physical change. There is always composition is fixed. If you have a carbon dioxide made in the sun, right, from the combustion in the sun, fusion or whatever reaction that might be, or CO2 coming out of any chimneys or from power points, carbon dioxide will stay as is, fixed composition, one carbon to two oxygen. Wherever you go on this universe, carbon dioxide, one carbon, two oxygen, correct? That's what we mean fixed composition, and that's what has been seen in the nature. So we don't see that's the carbon dioxide here, correct? On the Earth is CO2, and maybe CO3 on some other planets or meteoroids or stars. No, that's not. So law of definite proportion or law of constant composition, and to give you an example here, this is an example. Here's an example, you can look. So I took all those here. You have 1.166 grams of, if you look at this one here, that's chlorine here to 1 gram of copper, and this is and this is 1 gram of copper. So we have two compounds. We have two different compounds, brown compound and green compound, correct? So you have the green compound. It turns out to be, when you calculate, it will be copper to chlorine, correct? If you look at this, copper to chlorine, this is copper 1. Most of the compounds of copper 1, oxidation number 1 is green. Most of the oxidation number 2 will be brown or dark black. So copper will have its charge with 2. We'll talk about this. Always will be brown or will be black. Green always will be copper 1. So if you look at those data here, and if you look at the ratio between those here in the green compound, correct? And you take this example is not correct done, but here it is done. I think they correct the. Let me see, show you here. Here it's much better how to solve this problem. This is an example here, and let me go for the The first example, the calculation is correct, but the notes are not correct. Notes are, you will see it yourself when you look at the notes. So here we have compounds A and compounds B. Compound A has, this is carbon here, and correct, and we have oxygen, correct? This is the ratio between the number of grams of carbon to number of grams of oxygen, correct? So this is carbon here. Carbon. This is oxygen. So take another one. Second compound will have, this is oxygen. This is carbon. So, and you have the ratio between them. You divide by the biggest number up, the lowest number down. When you divide, you get the ratio is 1 carbon to 1.13 oxygen. So if you then when you divide for the next one, you get this one here. So if you look at this, oops, if you look at this, carbon is back here. If you look at this, carbon is always kept carbon as 1. It is so if you have this one here, I don't know why it's not real. I think carbon is 1 and oxygen is 2. So if you look at the whole thing here, this is oxygen here, oxygen. This is carbon. This is oxygen. This is carbon. Okay, so now if you look at this ratio here and then you divide both compounds, you will get a ratio between them is 1 to 2. It tells you that there is real compound looking like this. This is 1 to 1. This is 1 to 2. So this is following the multiple fixed composition. So if I have CO2, carbon dioxide, or I have carbon monoxide, CO1, so the ratio is 1 to 1. That will not come in the final exam or in the quizzes or something, but at least you know, if you look at the fixed composition, we don't have any fraction. We have to get rid of the fraction. So here, this fraction, you should not get any fraction. Get full ratio between the elements of both compounds. So you compare the first one here with the second one. It's between 1 and 2. So as I said, let's just show you this. This is the that's a fixed composition with some combination of elements. So the next is to look at the technology that Dalton really did not have. This here is an X-ray cathode, and this is an evidence for this experiment and evidence for, let me just have this one here. For electrons. This is an evidence for a negative charged particle inside within the atom is present. That's Dalton does not have this technology at that time. So the X-ray cathode is proven to us that there is a negative particle inside the atom, which is, if you look here, you started putting a current, correct? And the cathode is always negative here. The anode is always positive. What's happened? And he put this one here. Then this is the whole thing. He put the magnet. The south is your negative. The north is your positive. Correct? So he saw that there is, or the south here in this experiment is the positive. Let me see. What's happened is the electrons will come out of this and will be attracted into the so here it is. The electrons here, the high voltage, the electron will come in, will go through here, go through, and then we'll start the positive in the south here. There, the charge is already there. That's the positive. Can you see it here? What's happening to this? It does not take the positive in the top, negative at the bottom, and then they will see that the electrons are attracted to a positive, to the positive side of the magnetic field. Can you see that? So the electrons are here. Here they are. I don't know what's happening to this. That's here. Does not want to draw. Looks like really stuck. But anyway, so you can see that the beam of electrons are attracted to the positive side of the magnetic field. So we have, this is experiment has electromagnetic field, because you start with electrical current, and then through the electrical current goes into into a plate. The plates made of atoms. This current will go through the plates, and then the plates, getting whatever atoms there, will be stripped out of its electrons as beam. So those beam coming from the plates inside the magnetic field or electromagnetic field, because you have a electrical current. So the current is helping to brush out electrons of the atoms of the plate, and those atoms come in and they will be deflected. Correct? Deflected towards the positive side of the magnetic field. So they have to be negative charge, otherwise would not be attracted to the positive side. If they are the same charge, they will repel each other, so they will go the other way. They will go, but that's the proof for this experiment from Thomson. That's the atoms of the plates here. They do have negative particles called electron. It's negative charge. So take this on. Okay, so that's what it says there. Just look into this. The deflection of the electron of the particles from the plate is to the positive side, which is proven to be negative. You don't have to memorize all this, just to let you know that's how the whole thing developed to get into the definition of the atom. So it went through all those experiments through the years, over 50, 60 years or more, to get into the definition, which is the last one is Rutherford. We'll see his experiment, which is the last one, which is the best one. Then he took all the stuff, the work from the others, then he developed another experiment, and you'll see the picture of the whole thing. Millikan measured the oil droplet charges of a compound organic compound, oily. So he measured the charges, and then he had different drafts from A to E, and then he said he have seen that this charge as a multiple number like this number here. So it's like a charge every time appears, every time appears. So if any charge of any oily compound will give you multiple of this number. So it's like a magic number. It turns out to be, this is the charge of electron. This is the charge of the electron itself. So you'll see this, all this is supporting each other. Thomson, remember Thomson did with the cathode, remember X-ray cathode. He came with the model that's the an atom looks like a cookie, correct? Looks like a cookie here, which has positive and negative charge. But you know, this is missing something, and this is not the whole idea. This is not the whole idea. What do you think is missing here in his postulate about the structure of an atom? What do you think is missing? The neutrons, correct. So he did not even recognize there is the neutrons there without charge. So he looked at the X-ray cathode experiment. He proven to himself and to the others that there is a negative, there is positive charges inside the atom, and he came up with this cookie type of model, which is still, it's not bad. It's not bad at all. All this science always start step by step, and you will see that the Rutherford was building up all those given steps in one experiment, and he was at the end successful to explain the atom itself. Japanese scientist, he looked at the model differently, and he said, well, like a Saturn like atom, the atom looks like a Saturn. Then in the sense you have all this positive in the middle, and those negative charge is surrounding, which is very close. Now we are getting what? Closer and closer to the real thing. Again, it's missing here what? Neutrons are missing. The neutrons are missing, but this picture here is very closer than the cookie of Thomson. So, and here is the final work of Rutherford. Rutherford was honored, and one of the elements you can see Ru. So let's look at the Ru there in the periodic table. Ru is Rutherford. Somebody had spotted Rutherford. Rutherford is within the actinide and andinide, lactinide and actinides, and he is honored. Most of those elements are carrying out the names of scientists they have discovered or they have contributed to the area of chemistry and physics. So Rutherford came up with a good, excellent idea. So he has a lead box. This is a lead box, so just protect himself not to get radiation or cancer. So here it is. This is a lead box. Inside the lead has an isotope that's radiate positive radiation, which is like a protons, right? This radiation will go all through and hit a gold piece here. Very nice, like aluminum. See the aluminum foil? This is iron foil. This is gold foil. So why he took gold as an example for his experiments? Somebody will tell me why? Some ideas? We will learn later on that we have noble gases, correct? Group number 8, noble gases, they are chemically inert. But we have metals, correct? Are chemically inert, they don't react. And those are there, silver, gold, and platinum. Those three are inert, chemically inert. They don't. If you see in a cave, millions of years, does this cave have? It has inside it gold. Millions of years, the gold is still intact. Does it change? No. But if you have a piece of iron, this iron will be rust, will be gone, for example, or aluminum or any other element. But those three elements are resisting a change. They remain intact. And that's the reason he did not take any other element except gold. Other choice of his will be silver. Third choice will be platinum. They don't interact with nothing. So they are very stable and chemically inert, so they don't get. So what's happened is this radiation will come and hit this gold foil. Then we have more than two options. Some of the radiation will be deflected this way here. Here will be deflected this way. Most of the radiation will go through. Some of the radiation will be deflected the opposite way. Very few here. Few. This is the most here. Most. So, and he has like an X-ray film here. This is an X-ray film here. This is an X-ray film. Just show him the spots. All this is here. You'll see all these spots here, all over the places are spots here. So this here, you'll see lots of spots. It's not shown, but you'll see most of the spots here, all these spots here. They took this film, process it. We saw most of the aluminum, not aluminum, the gold foil is made of an empty space. I'm sorry, I was waiting. What about this, guys? I have to. I'm sorry. Just bear with me a little bit. I'll turn it off. I was waiting for a phone call. I'll turn it off. So I apologize. So anyway, most of the gold foil atoms are made of empty space. Why? Evidence for this? Because most of the radiation went through. Most of the positive radiation went through. Very few, they bounce back to the opposite side, to his side, to the side of the lead container, correct? So it means what? It means for him, this is positive. He knows this is positive charge. Isotope gives us alpha radiation. And it's coming back to him. That means it's hitting what? The same particle charge. So he called this one positron. He called this one not positron, he called this one proton. Positron will come back later on. Protons are particles inside the atom. That's when you hit them with the positive radiation, positive radiation will bounce out because positive and positive, they are repelling each other. Then he saw some few are reflecting the other side, correct? So it means that's inside the atom, something positive, that the radiation will come and be attracted to it. So three things he had seen. But he's lacking what? Somebody will tell me he's lacking what? What? Neutrons, correct? Did he mention anything about the neutrons? No. So his postulate, which is the best, ever best, that an atom is made of any atom, empty space, nothing, empty space. And this empty space, in the middle of it, is something has the biggest mass, very tiny, but very heavy, made of protons. And the electrons are surrounding outside this nucleus. in the speed of light, zooming, correct? Everyone's following? You have the picture of the atom? Okay, let me just make it smaller. So everybody had seen the movie called Honey, I Shrunk the Kids? Okay, so imagine that you are shrinking yourself in a submarine, right? In this submarine, you go with the submarine subatomic scale. So you'll be very tiny. You enter an atom. When you enter this atom, everything in front of you dark. You will not see nothing except hissing like a beehive. You hear this is the electrons are moving with the speed of light. And you are in the middle, or you are like a blind, you can't see nothing. Everything dark, everything's empty. And then all of a sudden, you'll come to the point when you center your submarine, subatomic submarine, of course, you hit something hard, you cannot enter it. That's your nucleus. And that's what it has, the protons and neutrons inside them, while the electrons are circulating, moving the speed of light around. Can you imagine this? And that's what really an atom. Atom is an empty space, nothing there, except the nucleus. It has the most mass of the atom, and then the small portion of electrons moving the speed of light around the nucleus, and they are almost massless. That's the reason they can move freely, easy. They can move. So if the protons will not move the same way as electrons move, correct? So that's the reason. So this is the postulate of Rutherford. Still, we have a problem with his postulate. He did not mention that the atom is missing what? Neutrons. Then other scientists came after him. He said, well, this is very nice. It looks very nice, the idea and everything, but something is missing about the whole picture. Something is missing, which is the mass. If I add the mass of electrons and the protons, they don't come up with the practical experimental mass determined by the experiment. Something is missing. So therefore, then this came in and then came up with something called neutron. Why is neutron? Because neutron, there is a particle there inside the nucleus, has almost identical mass of the protons, but has no charge. And therefore, the idea now, the whole picture is we have inside the nucleus protons and neutrons. Protons are positive charged, neutrons have no charge, right? And the electrons outside with the speed of light running around the nucleus. So why those electrons are held without collapsing? Because there is always forces controlling their speed, their rotation or the spinning around the nucleus. There are negative charges, and they are inside the nucleus. We have protons. Neutrons have no charge, but positive charge. So positive and negative charge are neutralizing themselves, correct? And the gravitational forces of the protons are pulling them, so they will not run away out, correct? It's pulling them towards the center, towards the charge. So and this is what the postulate here. That's the atoms is really empty space, and the nucleus is the most heavy part of the whole thing, and it hosts both protons and neutrons. Neutrons are charges. They have, particles. They have no charge. And here's the picture. You can see those are coming through. Those are coming through here. Those are coming through. That's proven as empty space. Majority of the radiation is coming through this empty space. Those are reflected here. Those are electrons. Those are deflected the other side. Those are protons, positive charge. So the protons are P, positive charge. Electrons are E, negative charge. And this is the gold atoms. So, and for his work, he was honored and he was given a name inside the periodic table. Rutherford is honored with the name there. You will see a lot of people are honored with their work inside, correct? So I think it's 104, around 104. The elements have the 104. If you look at the 104, you will find it there. But it's not mentioned here, but there. So anyway, any question you have so far? And yes, as you can see, this is, as you can see, this is just concept. What we are doing, just concept. Now, as I said, he rather made another discovery, or just it's like a conclusion. He made the structure of atomic structure of hydrogen. Hydrogen has only one electron and one proton, correct? One electron and one proton. Here, that's the scientist who came up by experiment and proven that something is missing called neutrons. Something is missing called neutrons, and the neutrons is given to the, let me see here, and then the charge 0. So we have neutrons, and then we have, this is neutrons, we have electrons, and we have protons. So protons positive, electron negative, and neutrons end with 0. 0 means 0 charge is neutron, correct? So they have the same, almost same mass of electrons. A little bit heavier, a little but not that much. Almost the same. If you look at the whole thing here. Friedrich, he came with the neutrons because he worked on determining the masses, the atomic masses or mass number of the elements, correct? So he came, there is missing, something is missing. They call it neutrons. Now, what's happened is that will give us to a new definition called isotope. Sorry, the isotope. Let me look at the isotope. The word isotope. Somebody will tell me what isotope is? Isotope. Well, it turns out each element in nature, majority of them, they will have isotope, correct? So not all of them, but at least up to 19. If you go for 19, then you'll have a lot of isotopes. But there are a lot of isotopes all over the elements periodic table. So isotope, the element can be found in nature, correct? With different modification. With what? Different modification. Why? It turns out to be electrons and protons are not changing in numbers. But in nature, you'll see the same element will change its number of neutrons. If you have a number of neutrons are changing, you talk about this element having isotopes. So isotopes is another modification of an element found in nature, not changing protons or electrons, but changing what? Neutrons, correct? So, and it's very important to know that up 19, element 19, then you'll see most of the elements will appear as isotopes. Now, in general, isotopes are not friendly because they can cause what? Radiation, and radiation can cause mutation of the cell and can cause tumor and cancer. So radiation, because of the fact, especially those are the larger one, actinide and lanthanide, they have larger mass, so they are not stable. So they'll start by themselves giving radiation without even doing, you are not doing anything for them. they will radiate in nature. When they get radiation, guess what? And it comes to the human body or animal body, it mutates the cell, creating a tumor, which it turn out to be a cancer at the end. So that's what the isotope is always related to. Okay, so here it is just to tell you about the modern atomic theory. We talked about it. That the atom is made of an empty space, and all the mass of the atom is inside the nucleus. Nucleus means center, the center of the atom. The center of atom has protons, positive charge. It has neutrons, no charge, and the electrons are spinning outside the nucleus, right, with the speed of light. That's the picture of the whole atom. So we included the charge. So here, just tell you just an example. If we expand the atom, so it will be like a football stadium, then the nucleus will be looking like small, tiny, a blueberry inside in the middle, central line of the stadium. Correct? So that's just an example. You can imagine if you expand the atom, and this is very big, and that's what the postulate. This is written by Rutherford in his notes. Look at his notes, real notes. He would put in the museum. He said if we expand the atom will be looking at all stadium without spectator, without players. The spectators are what? Are electrons. He said like this: the spectators are electrons watching, and in the middle central line is the nucleus. It's just small, tiny piece of blueberry. So that's his note. He wrote this one here, and you can see the diameter of an atom. That's done by the experiment. So 10 minus 10 meter, very, very tiny, small. So now, with this in mind, we ask ourselves, now how this the elements here inside the atom, how we measure their masses? Well, we measure their masses by a unit called AMU, atomic mass unit. Atomic mass unit is based on carbon. Is 1/12 of the mass of carbon. So that's the atomic unit. Later on, you'll see that's one AMU, one atomic mass unit, equal 1 gram per mole. 1 gram per what? Per mole. So it's not here yet, but later on you will see that's 1 AMU is equal 1 gram per mole. There's another unit, but it's not really used that much, which is Dalton unit, which is equivalent to the AMU, but it's not used. We use AMU instead from the Dalton ones. Now, if you look at the charge and the mass, you can see the mass of electron is 0.0091, 3091, 10 to minus 24 grams. So there is no normal balance will weigh this. You have to have a special setup for this to weigh this, correct? 10 to minus 24, that's a lot. I mean, very, very tiny, very, very tiny. So the protons are much heavier, but not much heavier, is 1.6 or say 2. I said 2 grams, 10 to minus 24. So almost, I said the mass of electron almost massless, and the electrons and protons are twice, just as you learn this way, twice the mass of the electrons. So you can see how small, tiny that really is. You look at the charge, the electrons has negative charge. You can see the negative charge here in front of the electrons. It is negative. Here is positive. It's the same identical charge, but but what's the difference is the negative and positive. Protons is positive charge, electrons negative charge. Neutrons they have no charges at all, and you can see all this in the AMU is given to you. So we are taking out the you see mass in AMU and mass in grams. You can see the relationship between them. The relationship between AMU and grams, it comes through the moles. 1 AMU is 1 gram per mole. And the mole is the ratio between mass over molar mass or atomic mass. So, any questions so far, guys? Any question? Okay, so until now we talk about concept. There's nothing calculation. The calculation will come in a minute. So now if you look at the periodic table, each periodic table, I think I do have one here. Periodic table. The periodic table, we can see let's look at the periodic table, and then we can share table. Okay, guys, if you look at the periodic table here, the periodic table is as I said, we can go through the PowerPoints, but we can just show you that the periodic table will have the name of the element, the symbol of the element, correct, and its atomic mass, and its atomic number, and it will have a characteristic of chemical change or physical change within the group itself. Now let's look at this. The periodic table is divided into three major groups. We have metals, correct? All these metals. We have non-metals. We have metalloids. They are acting like, in some condition, like metal. In some condition, they are like non-metal. We call them metalloids, so mixed. So, and if you look at this, let me show you where the metals are. Metals are the majority of the elements, almost 85 plus. So here it is. All those are correct. The actinide and andronide there on the bottom, I think. So here it is. All those are, and even this one here. All those, including all this stuff here. So everything that's metals. Okay. The non-metals are the green one. Those are plutonium is a metal. Let me take it out. Here it is. Those are non-metal, and the hydrogen is non-metal. Plutonium is, you can include plutonium as well. So, and those here, see it's different here a little bit. So then you have the stairs, the non-metal ones, the metalloids one. The metalloids one, if you look at this, let me get so start from here. See here. Oops. Select it. Here it is. Stairs, like it's stairs here, correct? So here it is. Silicon. Correct. Antimony. molecular. So it's like 1, 2, 3, 4, 5. Those are the green it's given to you here the color. So trying to do the color, but not all of them. The blue one is not metalloids. The metalloids, they have unique number. There are about 7 metalloids. So non-metal, metal, and there is no metalloids here. Let me go and show you the metalloids, and then we'll talk about. See here. Okay, so share this one here. Sharing. Here. Here. Now, if you look at this, here it is. You can't see them very well, but here they are. Can't see them very well, but anyway, so there are like stairs here. Why is not this one here is this one here. So the metalloids. So the metalloids are elements that they can behave either or. We can get the table. Let me get out of sharing. Metalloids in periodic table. Here it is. They are here, guys. Those are the metalloids. They are part of them. Is sharing? Yeah, we are sharing. There. There. So you can see those are metalloids. So what's really different those the metals from non-metals? Well, it turns out the metals are solids in general. Metals are solid in general. The non-metals are gases in general. Are there exceptions? Yes, there are some exceptions. And the metalloids, they can be metal or not, they can be non-metals. Can be metals or non-metals. So what's the difference between a metal or non-metal? Well, the metal comes a solid, shiny, correct? Cannot be compressed. If you compress a metal, we will break it. And it conducts electricity. The non-metal, on the other hand, is compressible. You can make out of it liquid and solid. It's in gas phase. Then it does not conduct electricity. This is very important. Maybe not in the book, but key of metal non-metal is the electricity conduction. Non-metal does not conduct electricity. Now, the metalloid will have the same characteristic of both, but when it comes to conduction of electricity, it does conduct electricity to a certain amount. So the silicon chip inside your laptop or iPad or our phones, it does conduct electricity up to 12 volts. After that, it will destroy your phone, correct? You'll destroy your phone or your laptop or iPad. So those, they conduct electricity, but to what? To a certain amount, not that much. The metals conduct electricity 100%. So if I put my fingers inside the outlet, the power outlet, I will get barbecued, correct? I'll get barbecued. Don't start laughing, but that's really true. You'll get barbecued. However, if you have air and you put anything inside the air, nothing will happen. The air will not conduct electricity. Otherwise, if air, oxygen, made of oxygen, nitrogen, can conduct electricity, then all of us will come walking like zombies, electrocuted, correct? We are not electrocuted, we walk normal, correct? So gases in general or non-metals, that's the key. they don't conduct electricity. The non-metals. The metals, they do conduct electricity. Now, the unique stuff here, we have hydrogen, because it has one electron, it put it at the top of a metal, and that's misleading. But we have no other choice. We have no place to put hydrogen, because that's element number 1, the periodic table. We have to honor this element by number 1, put it there in the top of group number 1, but it's not element, it's not metal. Hydrogen is non-metal. So then if you look at this, the metals themselves are defined into group number 1, and I hope it will allow me here. Yeah, we have time. Let me go. This is very interesting. You'll see. So here it is. Group number 1, they have a name called what? Alkali metals. Alkali metals means, it's an old Egyptian pharaoh's name. Alkali means they are making bases. They are what? Making bases. And even N, there is old Egyptian city called Natron. So the Na called natrium. We call it sodium in English, but usually come from the old Egyptian name, Natron village. So, and K came from the Kalium. That's not the Pharaoh, not the Greek. That's very modern. It came from the Greek, I think, Kalium. It's very modern, Kalium. So you can see the name. So second one, what we call the second one? Earth alkali. Earth alkali means find them in the soil. Earth means soil, alkali. They make bases, but you find them there. I can take dirt, put those group inside my bucket, nothing will happen. But I cannot take the first group, put it in my pocket. I'll be turning into fire. They will ignite in my body. They're not stable. Sodium, potassium, those not stable. They ignite because they react with H2O to build bases. Now, from here to here, guys, we call them transitional elements. Why transitional elements? Because they make very beautiful, colorful salts. So those are called transitional element. Called what? Transitional element. So they make a very nice colorful salts. Very nice colors. So you saw the glass, some glass looking, some glasses. This is transparent, but some of them blue, some of them green, some of them. Those are made of transitional elements. So the group number, this group here, it has no name, but it's called aluminum name because it carries out the first one. That's the element one, or the boron name. So this one is carbon group name. Now here we have some names. Here we have some other names here. Group number 8 here called inert gases. And number 7 here, fluorine and everything, called halogens. And oxygen, sulfur, and all those called halogens. Halogens, correct? And then we call the other one inert gases. I'll stop here, guys. I'll meet you then Monday. We'll have a lab this time. I want to see my students in the lab. Don't forget, have a lab next Monday.